Okay, welcome to GADEPS. Today we have Nikolaos Diamantis, who is going to talk about L-series associated to harmonic mass forms. Okay, Nico, go ahead.
Okay, thank you very much. And the apologies for the technical problems. It is a new fancy computer that the university gave me. It doesn't seem to work, but fortunately I have my co-author here, and he helped me. So as you see, it is joint work with Min Lee from Bristol, with Raji from American University of Beirut, and Larry Rolen from here. He's from Vanderbilt. And I will, what I'll start by doing quite quickly, since we have lost a bit of time, is to give some basic notation, and then I will present the context of the work and the motivations. So I start with the basic context. So for the purpose of the talk, K will be an integer, actually positive or negative. And we have the usual notation for the upper half plane, H. We will be using the hyperbolic Laplacian of weight K, although this will only be used once, and then you can forget about it. And what is also very important, some says more important than the Laplacian, is the action, which can be defined in our setting on SL2R, so determinant 1, on smooth functions on the upper half plane by the usual slash or stroke operator, as they defined very often. And we're going to see the involution, the Fricke involution, which for level M is going to be given to be represented in SL2R by the matrix that we have here. And this is going to be the basic notation. I think this will cover most of what we need. And in fact, we're ready to discuss the definition of harmonic mass forms, one of the various versions of it. We have N, which will be the level. We have psi Dirichlet character modulo N. We don't make any assumptions about primitivity or anything else. And then we have, we say that the harmonic mass form of weight K and character psi for gamma 0 of N is going to be a smooth function, differentiable, C infinity if you wish, which is defined on the upper half plane, which will satisfy these three properties. The first one is that it is automorphic with weight K and character psi. This is a very usual condition. It appears also in classical modular forms. The second one, which also appears in mass forms, for instance, elsewhere, we have the harmonicity that is annihilated by the Laplacian, hyperbolic Laplacian. And the third one, which is in some sense the most characteristic and has far-reaching consequences, is that it does not have moderate growth. It has, you can say, controlled exponential growth. There is some subtlety in that, but the version of the definition we'll be discussing here, we'll be using, is that expansion of the f function slashed by any element of SL2Z. So in particular, in the case that the gamma is simply the translation, or even the identity, this will mean that f of z is up to a principal part exponentially decaying. But we have the principal part, which will be exponential. And this small addition really has a lot of consequences. Just to give some very, very brief overview of the kind of things that this allows us to tackle. So it is by means of such objects that we managed to prove, we meaning mathematicians, the Andrews Dragonet conjecture, or about partitions, Dyson's ranks. These were some of the first striking results which were deduced by the study of such mass forms, harmonic mass forms. I should probably say that this is essentially the dual theory to the famous Mach modular forms theory. And since then, there have been connections to L functions of cusp forms, to special values, or even values of L functions of cusp forms, to mathematical physicists. It has been a very broad subject by now. And we can safely say that the extra amount of freedom that allows us to go to this kind of applications is the exponential growth of these modular forms. A piece of notation, we write H sub k of n comma psi for weight k harmonic mass forms with character psi. And a technical but very fundamental element in the structure of those forms is the Fourier expansion. In some sense, you can call it generalized Fourier expansions because you don't use only q to the n, only the exponential. So the way that we can write such elements of the space H sub k is that we're going to have a piece which traditionally we call the holomorphic part, which looks the familiar Fourier series, except that it starts from, in general, from a negative exponent, what we write as minus n0, where n0 is positive. That's a somewhat familiar part. Less familiar part is the non-holomorphic part, which is expressed in terms of incomplete gamma functions, together with, of course, e to the 2 pi I n z. Now, about this incomplete gamma function, there are a few things to be said because we require the essentially analytic continuation of the incomplete gamma function. There can be some interesting phenomena that occur even on the basis of this analytic continuation. In any case, that's the expansion at infinity, and we can have similar ones for the other cusps upon slashing with other elements of SL to Z. So this is the Fourier expansion, and already by looking
Nico,
at that...
maybe just at the beginning of your talk, you put the smooth function. So actually, they are real analytic function, no? Or
Yeah, that's a... I mean, I use all of these things interchangeably, but yes, this is real analytic. Yeah, you're right. That's because in any case, we have something slightly more precise. We know that it is harmonic. So we have this property too, but it's real analytic, yes.
Well, that guarantees it's, yeah.
Yeah, exactly. That's why I said it more specific. That's the... So the by looking at this Fourier expansion, you can specialize to forms which we call weakly, the space of weakly holomorphic cusp forms. This contains two specializations. The first one is that we can ignore this non-holomorphic part. It does not contain, these BNs are all zero. So we are left with something which looks familiar, the familiar exponential, but the difference is that, of course, we start in general with negative exponent. So with this n0, the minus n sub 0. But, and that's a slightly subtle point, which again has surprisingly far-reaching consequences, we also do not allow non-vanishing constant term. So it will be holomorphic harmonic mass form, but the constant term at all of the cusps will be vanishing. And this is what qualifies this word cusp form. Cusp means that the vanishing term is, that we have the vanishing constant term, but not that it decays exponentially at infinity. And this can be confusing at first. So that's the notation, which again will reappear a couple of times. So now some comments about that. The key property, key in a sense that it causes some problems in terms of the title object, the L functions, is that we do not have polynomial growth for our Fourier coefficients. What we have is some kind of a hybrid exponential growth. So it is e to some positive power times square root of n. And the square root of n is really what is required. We are really at a place which it's not wildly exponential, so to speak, but also not polynomial. And the first consequence of this fact, which can be proved by various methods, even by circle method, that's one of the ways to look this that this is the correct growth. We cannot define L functions in the usual way. For example, we couldn't say, even if we ignored the negative n's or the possibly zero coefficients and so on, even for if we're restricted to the positive terms, we will not be able to define that, no matter what S was, a real part of S was. So that's not the way to start the definition of an L function associated to weakly holomorphic forms, generally to harmonic Maass forms. However, let me make a pause because I don't, the way that it's set up, I don't see any faces so that I can see if someone is a bit confused about any. So if there is any question, here's your chance. There's no way to make it.
Yeah, go ahead.
I don't know how, but
okay.
It seems they can hear you. So.
Okay. That's
yeah, we can hear.
Okay. So the issue is L-series, how to define them. And in the special case of weakly holomorphic cusp forms, we have, there exists a definition of L-series, which was defined, it appeared in a paper by Brinkman, Fricke, and Kent, and Brinkman attributes it more to Fricke's thesis. And the way it works is by using something which is used very often for numerical calculations, even in the classical setting. So we start with our Fourier expansion, again, weakly holomorphic with trivial character. We don't need to worry too much about that. And then we pick any arbitrary t0 positive, and then we can write down this expression. I don't know if you can see the cursor, if it is visible. The Ls of f is equal to something which, on the one hand, does contain something familiar, a of n divided by n to the s, but we also multiply with an incomplete gamma function also evaluated at s. That's the first piece. And then what they do is they also symmetrize it. This is necessary for that specific construction. Now, the interesting thing is that this definition is independent of T0. No matter what T0 is, it's going to be the same L function. That's why we do not include it in the notation. And this is almost equivalent to the fact that F is modular, is automorphic. And so that's the first element. But this is an expression which can be used, in some sense, it is a little bit like the approximate functional equation technique, even in the classical cusp forms. But that was a definition which did have some applications. We have even used in a work that I made with Brinkman and Stefan Ellen, where we studied the inner product of general weakly holomorphic cusp forms and the connections with L functions of standard cusp forms. So it definitely has applications, but the problem is that there were two constraints for the purposes of a more classically oriented theory of L series. Okay, the first one is, of course, that applies only to weakly holomorphic cusp forms. But
maybe Nico.
sorry,
So
yeah.
the idea of putting gamma near to n is due to who? The Fricke?
Yeah, the idea of no, to write it down in this way is due to Fricke. Fricke, I don't mean the Fricke of 19th century.
It is it's a new
sorry. Yeah, it's an idea of Fricke, who is a student of Zagier. I think he graduated
okay.
years
It's
ago.
not the old Fricke. It is
No.
Karl-Heinz Fricke.
Yeah, Karl-Heinz Fricke.
Okay.
Yeah, it would have been interesting. Who knows? Maybe you can see it in Fricke, in old Fricke. But yeah, the actual definition appears in a slightly different form in Fricke's dissertation. So now since you mentioned it, what this gamma function does is that it compensates for the exponential growth of a of n. It has suitable growth to cancel that out. And then, in fact, that's another weird element which will appear. This we don't even need to bother with analytic continuation. This series applies to all S. That's the interesting thing. So we go from one extreme to the other. In the naive definition, you can't define it for any S, no matter how hard you try. But in this way, you have absolute freedom for S. It's defined automatically for all S. So the main difficulty in going ahead with the usual theorems about Converse theorem and so on and so forth was that you couldn't make a statement like the classical Converse theorem where we say, suppose that you have the usual conditions, EBV, analytic continuation, and above all, functional equations, then you can deduce that the corresponding Fourier series is modular. In this case, you can't say that for a reason which is almost automatic, almost tautological, because all of these conditions are written inside the way that we write down the L function. So you cannot ask for this hypothetical statement if it has a functional equation, then we have something, because it has it automatically. So already from that phenomenological standpoint, it is impossible to try to even formulate anything about Converse theorem, at least of the usual version we have. So meaning Larry Rolen, Wissam, and Min Lee and myself, looked at a slightly different approach, which in a way is related, I will make some comments about that later on, to the approach of distributional L functions or test functions, somewhat having the flavor representation theory approach, but as far as we could tell, it could not, it wasn't so obvious to reduce one to the other. They seem to be somewhat parallel. So I'll start by the description of this construction. We start with Laplace transforms. So we look at the phis. For example, we can even think, and we will be thinking later on, of compactly supported real analytic phis on the real, positive real numbers. And then we consider the Laplace transform in the very classical way that we write it. And for the time being, we do not worry about which S make it converted absolutely. This will depend on the specific application. The second piece of notation we will be using, this is in some sense, you can say a remnant of Melen transform approach, which we have by now replaced by Laplace transform. We write phi sub S of x to be phi of x, this test function, this general, potentially compactly supported function, times x to the s minus 1. And this collapses to f itself when we set s is equal to 1. So this is notation. Now, the definition, in its simplest form, we look at the harmonic mass forms. We look at its Fourier expansion, the one that I stressed its importance of. And now we define the L-series as some kind of functional a mapping from a certain set of functions like the ones of the previous slides, this potentially compactly supported phi, into some numbers, actually. So we have replaced the n to the s, or the incomplete gamma functions in the previous versions of L series, with the phi and specifically the Laplace transform of those phi's. So in other words, the variable of the L series is not anymore a number, but this phi, which can be suitably restricted in any form you want. For the time being, we can be flexible. We can say that we define it for each piecewise smooth phi from R to R plus to C, for which the right-hand side converges absolutely. Actually, I should have stressed the absolutely. So the first part corresponds to the holomorphic part of the function f, and the other one corresponds to the non-holomorphic. And the natural question to ask, among many other questions one can ask, is how it relates to the classical setting. Is it something completely new? Why does it deserve to be called L functions? And all of these things. We will discuss this as we move on to remarks. So the first remark is that we can apply it, we will see how it's applied to more general series of this form. After all, we want a Converse theorem, so we want to be able to write down something like this for something which we do not know yet whether it originates in a harmonic mass form. Another occasion that we will also see is twists of twisted expansions of this series. So it can be generalized in a nice way, in a direct way, in more broad setting. The second one, I already hinted upon that, is that I allowed myself to take any functions for which the formula would make sense, but the one very important for our purposes subclass of such functions is the compactly supported smooth functions defined in 0, infinity. We exclude 0 in a crucial way. So now I'm ready to answer this hypothetical question. So it does contain the classical definition. If we now restrict to F, which is no longer harmonic mass cusp form, which is not even weakly holomorphic, if it is honest holomorphic classical cusp form, then we can simply take phi to be essentially x to the s minus 1 times some functions of s alone, and then we plug it in, and what we are going to get is exactly the classical Dirichlet series, but now the real part of S must be k minus 1 over 2 in the first instance before we do some analytic continuation. But in this case, we see two things. First of all, that our definition does contain the classical one. And the second is that it also works, that the definition works also for non-compactly supported functions. So as I said before, it is definitely works. It requires a small estimate. It always works if the function phi is compactly supported, even with the growth that we mentioned before, this e to the c square root of n. But it also works for classical cusp forms if we select this specific test function. And that's when we really have as parameter s rather than this general function phi. So that's the first example. I also mentioned another L function for weakly holomorphic forms. Now, in this case, it is slightly more subtle in the sense that it does contain it, but that's a crucial element. If you recall the comment that I made when I presented this, let's say, previously defined L-series, now it's going to appear in a non-symmetrized form. And now the appropriate function to plug in for phi is going to be phi sub s, the one of remark 3, times essentially the characteristic function of the interval t0 to infinity. And then if you plug it in there, it's going to boil down to the one which I call Freike's definition of L-series associated to weakly holomorphic forms. So it does contain, it belongs to the same conceptual framework as the previously defined L functions in the classical and the weakly holomorphic context. So these are the first remarks. Now, as I said before, with the previous definition, the functional equation, it's not that it was trivial, but it was built into the function. Now, in our case, it is no longer the case. It's not a trivial statement, and we have to see how it works. So that was the first theorem. So there is a number of stumbling blocks one has to take into account. Of course, the issue of the exponential growth of the Fourier coefficients, but also we have to take into account the fact that we're not in a holomorphic setting, but we have also a part which is more real analytic, as you mentioned before. And for the Converse theorem, that's crucial. We need to take that into account in general. And that's why we're going to have essentially pairs of functional equations, not just for the L functions, but also for some kind of dual of that L function. Okay, let's see how it works. Our parameters K in Z, although, as I will say later on, we can extend to half integral weight K, is very important for our application future work. N is the level. Psi is a Dirichlet character mod N. And we consider an F with, by now, familiar Fourier expansion for character psi. And now for any character, not necessarily primitive, modulo D, where D is coprime to N, the classical setting so far, we define the twisted L functions of F. So this is going to be almost the same as the classical setting. The only thing that is somewhat different, I will explain the reason for this technical difference, is that instead of multiplying with chi of n, as we would normally do in the very classical case, we twist with a generalized Gauss sum, which is at the bottom of the slide. The reason for that is that it allows us, when we move on to Converse theorem, to avoid having to deal with only primitive characters. And this is a trick which goes back to Michael Razar when he proved in the classical setting his Converse theorem, where he used only finitely many characters. And this was a crucial, simple but crucial trick that he did. So we twist with the Gauss sum, not with the character. Now the rest is as before, apart from this twisting. And also we have to account for the fact that's purely technical, that we have modulo D character, and that's why we divide with D in throughout, where the N appears in the functions. Now the second one,
are these evaluations at some S?
No. This is for any. The evaluations are for any F. So you say I have
this S parameter of the L function.
It applies there too, of course, but it is more general than that. So in the case of harmonic Maass forms, we will require not this S thing, although it can appear, but we will require things like an example, which we do mention in the papers, the Dirac function. So that's an example that we have where there is no S. So the phi is any compactly supported function, if you wish. So that's the unusual feature of this construction. We don't think in terms of functions on the complex numbers, but in terms of mappings on spaces of functions.
That's why you define the function phi s, no? Because
but this is a special case.
Okay.
You don't need the S, but this phi can be anything, which can have nothing. Like some characteristic function of a tiny interval, for instance. That would be perfectly fine. And the same goes for the next one, which is the dual of that. So if we have one piece which is inherited by L f of chi, comma phi, but we also subtract with something which looks like a little bit like a derivative, because we have an n multiplied in front, in this case. And this, as I said, is in order to account for the lack of holomorphicity. So anyways, we have these definitions. And now for those twisted L functions, the theorem is that we have the following the pair of functional equations. Now, what we could ask is two things. First of all, what is the Contra Gradient? The Contra Gradient does not have any issues. It is f slash k sub n, as in the classical case. But what is more interesting is if we had S, as you mentioned a few seconds ago, then we would be able to say, yeah, we go from S to k minus S. In this case, we have something more general, I will put in those terms. We see this process of going from S to k minus S is mapped, if you wish, corresponds to the process of going from phi to a new function phi on the same space, which is defined by this evolution, which I put at the bottom of the statement. Now, if we plug in f sub s instead of phi, then we're going to end up indeed with k minus s. So this, in that special case, does translate to k minus s. But in general, if phi is anything we want, and that can be, it's going to look like this. But if you plug in phi sub s, then you indeed get the familiar expression. So these are the functional equations, both for the twisted L function and its companion, L f prime, where again I should stress that the prime does not mean differentiation, although it has this flavor. And again, I will make a pause to see if there are any questions about this, because I can understand it can be a bit unfamiliar. Okay, so what I'm going to do is, before I make any further comments, I'm going to show you how this can be turned into a converse theorem, what the converse theorem for that is. And the converse theorem, which was, let's say the motivation. We want to find an L function which has the usual features of L functions, or L-series, which means converse theorems, and the connections with classical L-series, etc. So the converse theorem that we managed to prove goes like this, constructing the following way. We have the usual things, n, psi, Dirichlet character modulo n, and we look at two pairs of sequences in reality. The first pair of sequences is denoted by a sub 1 of n and b1 of n, and the requirement that we have is that it should have this, as I called it, weak exponential growth. Maybe that's the best way, because we have the square root of n. And now we also require a second pair of such sequences with the same property. And then for each of these two pairs, we write down a series in the way that we saw before. So the first one, F1, will be consisting of A1s and B1s in exactly the form that we had before, the classical setting. We don't know yet what it is. We would like to show that, to find conditions strong enough to show that this is harmonic Maass form. So that's the aim. And now the conditions are going to be in the spirit of Razar's, actually, formulation of Van der Waals Converse Theorem. So we let D not do not range over all the D's, but simply in the set 1, 2, up to n squared minus 1. So we require finitely many characters. And then we take chi to be a Dirichlet character, which does not need to be primitive. That's what I mentioned before. For each D and chi at any compactly supported, now we can safely focus on compactly supported phi on the real numbers. We assume the equations that we saw in the previous theorem, except that F1 goes to F2. We do not know yet the relation of F1 with F2, but other than that, everything looks visually at least the same. And that's a requirement. We also require L prime to satisfy the same functional equation, but with a minus in front. So this we require for all chi's and actually for all s. And now the s does appear. So we have two parameters. So the phi can be anything we want, and the s can also be anything we want. Now the conclusion is that the function f1 will be harmonic Maass form of weight k and character psi, and also that f2 will be f1 slash wn. And so now a first remark before I go to the official remarks, because I can imagine that this will be a question, is there are some differences from the classical Van der Waals theorem or even the Hecke theorem. We do not say anything about the analytic continuation. And the reason for this is inherited essentially by that older, the previous definition of L-series associated to weakly holomorphic forms. And in our case, can be expressed in terms of this keyword compactly supported. The fact that this compactly supported, that we look only at compactly supported test functions, guarantees that convergence is not the issue. The series by themselves are L functions, so we do not need to make any analytic continuation. So it's a purely Dirichlet series theory. And also, we do not require anything, of course, about the bounded in vertical strips, again, for the same reason. These are all taken care of automatically. And the last thing is about the LF1 prime. If we had the Maass forms, we do not require this condition. Why do we require it in the case of harmonic Maass forms? So the reason is the following. In the case of Maass, classical Maass cusp forms, we can split the space of Maass forms into direct sum of even and odd Maass cusp forms. And in each of those spaces, you can focus on this theorem, and then the condition LF1 prime is deduced directly by the functional equation for L itself. It's by an accident that it occurs because of the symmetry in the case of even or odd functions. In our case, we're more general. We do not have this kind of splitting into even and odd in this form. And that's why we require to have a pair of functional equations. Okay, so now I go to some further remarks. As I said, all of these things can be, and it is needed for current work we're doing. For half-integral weights, it is in terms of technicality, it is much more complicated than the integral weight, but this is a very interesting case because it has arithmetic. The second point is, as I said before, that in all compactly supported functions satisfy the direct theorem. This is a comment for the direct theorem. The third one is sequel to what I mentioned a few minutes ago, that in the case of weakly holomorphic cusp forms or weakly or holomorphic series, the functional equations for L f prime are not needed. They are essentially vacuous. So to go back here, if we restricted our data into A1 of n and A2 of n and B1 of n were 0, if we had only holomorphic part, then we could draw the same conclusion, but requiring only the functional equation for LF1 and LF2, not LF1 prime. This is only to cater for general harmonic mass forms that we have the LF prime. Now the context of that. As far as we know, the only Converse theorem for harmonic mass forms was proved actually a few months ago by Shankar and Singh, but this included only forms of polynomial growth. So although it would cover the case of the non-holomorphic part, it would not address the case of the exponential growth, which is in some sense the more common case, especially for applications into arithmetic. And that was our main effort here, to address exactly this exponential growth. And that in turn is what necessitated things like looking at compactly supported functions and things like that, which were not required in the work of Shankar and Singh. Now, in an opposite, in a somewhat different direction, the context of the work in which we see it, and this inspiration, in some sense, comes from what I hinted upon in the beginning. There have been some investigations on classical L functions or even the Selberg class by people like Andy Booker, Steve Miller, W. Schmidt, and also Miyazaki, Sato, Sugiyama, Ueno, where they used also test functions, and also in the case of the last joint paper of Miyazaki, etc., they also used, in some cases, also the Laplace transform. But this notion of L functions at distribution, there is even a paper by Andy Booker with exactly that title, has appeared in a different context than the question, the work in progress that we have, is to see how it matches, how these different approaches on the same basic philosophy of distributions and test functions can match, how they can interact so that we can get new results. But for the time being, what we have seen on the superficial level is some kind of parallel work among all those approaches. How am I doing in terms of time? Am I out of time?
I don't know how long.
Yeah, I think no, 3:22. So I think I have.
I think you have 10 minutes more.
Yeah, I think I will be able to finish even earlier. So now an application that I wanted to discuss. It is again something which appears in some sense, as far as we know, for the first time in this theory of harmonic mass forms and mock modular functions, something which comes from a more classical analytic number theory technique, a summation formula. So let's see again the context. First of all, we simplify everything. We now assume that the level is 1. The character is trivial. And we consider a fundamental operator in the whole theory of harmonic mass forms and the mock modular forms, a shadow, as they call it, operator xi. of weight 2 minus k of f. Now, what happens is that you get this operator, it's not really it's a map, maybe to be more precise, takes elements from the space of harmonic mass forms and maps it into holomorphic functions. And we know from work by Funke and Brunier that this is actually onto this surjective map, but a big question that appears in the theory, especially for arithmetic applications, to show that to have some explicit lift, as we call. So the problem is, given an f, which is a regular cusp form of weight k, can you find as explicitly as possible a function g, which is harmonic mass form, whose image is equal to f. And very often, many of these, to some extent, even this Andrews Dragonet theorem was essentially solving this problem. Behind was exactly this issue that we had. And so perhaps ambitious idea would be to be given a Fourier expansion of f and to be able to have a formula for the Fourier coefficients of g. That's a bit too much to ask for, perhaps even not desirable, because it would perhaps trivialize the theory. But what you can do, what we did by using the theory that we developed in this theorem already, the direct theorem was enough for that, was to find a summation formula, which is doing the following. We start with f, we know the Fourier coefficients, and then we get a relation for the Fourier coefficients of the function g for the harmonic lift in terms of an arbitrary set of test functions, which includes, in fact, the hard part of the harmonic mass forms, which means the automorphic, the holomorphic part. So let me be more precise, and then we will I'll explain how this is done. We start with f, which is cusp form of weight k, with the Fourier expansion that it should have. Suppose that g is the harmonic lift, in other words, psi of g is equal to f, which we know that it exists. It's going to, we know what Fourier expansion it's going to have. The c to the minus, the Fourier coefficients of the minus part are directly obtained by f. So this is not the issue. What is mysterious, and that's where the arithmetic information is contained, is the c plus, the Fourier coefficients of the holomorphic part. And that's what we would like to know in reality. How can we know? Ideally, we would like a formula of the type c plus of n is equal to square root of a of n or something like. But of course, these things are silly. But what we can get is a summation formula. We can say that for every piecewise smooth, compactly supported phi from R to R, we have this trace summation formula, whatever you want to call it. And it is going to have, in the left-hand side, we have the c plus of n, these mysterious terms. We have also this term which is dictated by phi of s. This is an integral, which can be even, in many cases, computable explicitly. So take almost some kind of series or even a linear combination. And this is expressed in terms of things that we know, in terms of a of n, which is what we wanted, in terms of the phi functions, of course, and in terms of Whittaker hypergeometric functions. This is all in the spirit, and even the technique that was proved was very similar to the standard ways that the people, again, like Miller and Schmidt, prove summation formulas, but even people like Blomer, there is a huge tradition on summation formulas and even eventually trace formulas. So this tells us that even though we can get an information for individual c plus of n, which, as I said, is perhaps unrealistic, we can get at least a relation for each compactly supported function in terms indeed of A of n. And this was the first application of actually direct theorem that we obtained. Other applications, which are mostly work in progress, is in constructing new operators for subspaces of harmonic mass forms, or also proving things like Rankin-Selberg properties and so on. So it is. It seems that this approach can allow us to do many things about harmonic mass forms in a direction which has not been looked at as yet. I think I will stop here.
Okay. Okay. Thank you, Nico. I was to ask a question, but you start. Yeah. Okay. Anyway, I have to ask any question before I ask my question.
Yes, I have some question.
Okay. Okay. Pierre.
So, yes, I have a question that is motivated by some problem that actually in a paper with Steve D. Miller, and Michael Green about solving some. So we have a lab, the Eisenstein series, they are eigenvalues of the harmonic Laplacian, but we get from string theory something that has inhomogeneous term that is a square of the E3 Eisenstein series. And in fact, that is a case where we actually use some of the method you described to get the Fourier coefficient. Playing with the method of orbit. And okay, so we solved it, but it turned that there is another formula which shows that actually some Fourier coefficient vanish. And Steve Miller cannot prove that. The thing is that there are physics considerations. So in a sense, so I don't know if I can, maybe, can I share my screen? Because I just want to show the equation I'm looking at.
Yeah. If you want
Let's stop present.
Yeah, we stop present. Yes.
Yeah, go ahead.
Yes. Infinite. Yes. Okay, just a minute. I just need to make sure. I think that's the right. Yes.
Right now, because it sounds interesting.
Yes. Right. If I was in front of, you see so the formula is like this. So this is the, make it bigger.
Can make it bigger? Yeah.
Yes, is it? Right. So you see, so this is the usual, harmonic Laplacian, and then this is the standard non-holomorphic Eisenstein series, which is defined. Okay, just a minute.
That's the Zaghi Eisenstein.
Yeah, it's the Zaghi Eisenstein series. Okay. Yes.
Yeah.
And the thing is that, okay, so we try to solve, we have some way to get the Fourier mode, Bessel functions, standard story, right?
Yep.
But okay, I'm going to stop because I'm not giving the talk. But so the thing is that what we did is right. It's a solution. Yeah. But apparently there are properties, some vanishing coefficient of the Fourier series that we didn't see, but that have been numerically found and motivated by physics, but we can't really prove mathematically. So in a sense, this is a class of functions. So this is a generic class of these new modular forms, and it connects with some work by Francis Brown about.
Yes. Yeah.
Okay. And as well some work I did with Spencer Bloch. So the thing is that it's very important for us to know how to efficiently compute the Fourier coefficients. So I don't know if you have looked at this problem.
Yeah,
what's the name of your paper? Is it
the name of the paper is so it's called SL2 invariant and the instantaneous contribution to the d to the 6 or to the 4th interaction. So the FTH number is 1404.2192 is with Steve D. Miller and Michael Green. So, and in a sense, it's but there are a lot of works of on this kind of differential equations, and so there is the same question for higher rank as well. So as well look at for the Eisenstein, some equation on EA87, but already the rank 1 is already very rich. So Zagi's method is not, totally, it's working, but it's not the optimal one.
Yeah, I see. No, this I could imagine that these methods would work because, especially what you mentioned with this work of Francis Brown, because also he uses there is this he calls them real analytic or non-analytic modular forms, on which I have also worked independently. But I think these methods, definitely these methods would cover that case because of the exponential growth, which has been the problem in Francis Brown's explorations. And this one does address, we did not look at this real analytic forms, but I did mention, we mentioned it in the paper that they should work, but that's something that we would like to look at. So I could imagine that even in the case for the Eisenstein series of this type, it might be possible to say something. I don't know if we would be able to have a formula like this kind of simple thing, but vanishing, it could be.
So you want to know the form satisfying the equation that you showed on the screen, that doesn't have any vanishing Fourier coefficients or something like that?
No. The thing is that So the thing is that the question is, so if you are in higher rank group, there's the notion of waveform set. So the vanishing support of the vanishing, the place where the Fourier coefficient don't vanish, right? Okay.
Yeah.
Which are given connected to orbit and nilpotent orbit. In rank 1, of course, it's difficult to have this. So it happens that there are Fourier coefficients that vanish that we didn't see, in the equation we write. So it's a rewriting of what we had, but in a sense, there are some vanishing we didn't see. And so this test function, so we use test function again, and as well Steve used as well in his work on sphere packing and things like that. So there maybe there is something that we missed, but as I said, I'm wondering if there is a...
No, that's a worthwhile question.
Yeah,
if it's
definitely.
possible to account for that, yes, that's. I had not seen that in this. I had not connected with exactly this part. There was this kind of connection with the broader ideas of Francis's, but for this one we did not go that. So we're going to look at that. Actually, that's
okay. If you have anything interesting to say, yes,
absolutely, yeah, that would be great. Yes.
Yeah, and